Hello everyone, how are you guys doing? Today I want to talk about the concept of derivatives and what they are really. I'm sure you've wondered the same thing, and you probably think that it has something to do with change, which you'd be correct to think. They have everything to do with change. Derivatives are essentially functions that model change between different variables. Let's say you have something like y and x. When we say that y is a function of x, it implies that, well, your x is an independent variable, some value that you arbitrarily choose as your input, and you get something out, your output. So your y, that is to say that your y depends on your x. Your y is a function of x. Okay, so let's say we graph a relationship between y and x. Y and x can be really anything in terms of physical properties. But let's just look at the math here. Let's say you have a curve, and we want to know the change in y with respect to the change in x at some interval between 2 points, like so. So we'll call this x1, and we'll call this x2. So these are our inputs. So if we put in x1, let's say we get out y1, and x2 for y2. I don't know what they are exactly, but we want to stay general so we can derive something here. Now if we connect the 2 points like this, you'll notice that we get a secant line. And if we measure the slope of a secant line, we know that it is rise over run. That is just called m, the slope. That does measure change. So our rise will be y2 minus y1 all over x2 minus x1. That is to say, our delta y all over our delta x, our change in y all over our change in x. So we have a ratio to represent change in y over change in x. Pretty straightforward. All this means in English is the change in y due to some change in x. So we can measure change of a variable y over some interval of x. But what happens when we make delta x very, very small? What happens when we make that interval very, very small? Let's draw another curve, but this time, let's make the points really, really close together, like so. So very close. We still have our x1 and x2, and we will still have our y1 and y2. But I want you to pay attention. What happens when we make this delta x so very close? The difference being so very, very small. What happens then? Something interesting happens. Because previously we were mentioning change over an interval. That's to say that is the average change, and we'll talk about that in a minute. But what's happening here at this point, if we zoom in a little bit, we essentially see, well, the same situation. It's just 2 points, and our 2 points are x1 and x2 still. Those are our inputs. You plug in x1, you get some y value, we'll call it y1. Plug in x2, we get some y value, we'll call it y2. Straightforward. But if we connect the dots, the 2 points like so, we get the secant line, just like we had in our previous example. But if we zoom back out, it really doesn't look like a secant line. Rather, it looks like a tangent line, a line that only touches one point of a curve. The intervals are so close together, it might as well be one point. But because it really is a secant line, we can still use the idea of rise over run. We'll say that y2 minus y1 all over x2 minus x1 is our slope of the tangent line. But we want to be a little bit different with this. Because we made our intervals so small, our delta y and delta x, our delta x is so small, let's call it something else. I don't know. Let's call it dx. That is to say that there is a little bit of change in x, which results in a little bit of change in y. All that means in English is a little bit of x, a little bit of the x interval, a little bit of change in x. Whereas previously, delta x is some change in x. It can be any amount of change, but it's an obvious amount of change such that you can see a secant line that passes 2 points of the curve. But now our dx is so small that our line only passes 1 point of the curve. It looks like that. So our slope is dy over dx. And I'm sure you're familiar with that term. And what it says in English is essentially the resultant change in y due to some change in x, due to a very small change in x. Not to some change, but to a very small change in x. What happens when we change x a little bit? What happens when we just nudge, just from x1 to x2, we just nudge a bit? What happens when we do that? Previously, we didn't do that. We specified that the change can be, well, anything. It's some change. And when we say that, we mean that this change is average. So the average change in y means that y is changing over some interval, in some way. So we can find average change with the idea of secants when delta x isn't so small, when you're just working with intervals of x. So the key word is being interval and average. The average change in y over some interval of x is delta y over dx, or delta y over delta x. Whereas with dy over dx, our delta x is so small that we're practically measuring change, but at an instant. The instantaneous change in y at a very small change in x, so small that we can call it a point, at some point at x. So the key word is being point, instantaneous. Do you see how I'm differentiating between the idea of secants, average change, and the idea of tangents and instantaneous change? That is what derivatives do. Instead of looking at average change, we can look at instantaneous change. Let's look at a particular example. Let's say we have distance as a function of time. Let's say we model your distance over time. And it looks like that. It looks like a curve, like so. And we want to know, well, okay, what is the speed? What is the speed exactly at a certain point in time, t? What is your speed at this point? I don't want to know the average speed. What is your speed at this point? How much are you moving? How much distance do you cover at this amount of time? At this point in time? The question doesn't even make sense, does it? How do you cover distance when no time has passed? But the idea works because it's approaching a very small amount of time. It's approaching a little bit of x, dx, dt, which results in some change in distance, ds. This is the idea of instantaneous change. So when we draw a tangent line to the curve at that point, we get ds over dt. Whatever that may be, we call that v, and that is velocity, or speed. This is to say that this is the instantaneous change in distance over a very small change in time, the instantaneous velocity at some point in time. Yes, you can measure the change in your distance at a point in time, because it's not exactly a point, but it approaches the idea of a point such that the change is instantaneous. That is the idea of derivatives. That is what derivatives